All right, so let's do a little bit of synthesis strategies before we jump into our worksheet. There's a lot of unusual reactions from this chapter. The main thing I want you guys to know is the mechanisms, but I do want you guys to be able to move through things quickly. So let's be able to first decipher all the alpha functionalization reactions. So this means we're going to functionalize the carbon adjacent to some other carbonyl. The first one we saw was halogenation. That was where we had typically a ketone. We treat this with acid and bromine. And we can really easily halogenate over on this alpha carbon. Oops, sorry, this should be a Br. So this is our alpha halo ketone. There is one other thing I did want to point out. With methyl ketones, what can you do? Yeah, the haloform reaction. So that's a variant. The haloform reaction can convert a carboxylic acid, or sorry, a methyl ketone to a carboxylic acid. Typically, the conditions for the haloform reaction are a little bit different, though. You use sodium hydroxide, your halogen, you exhaustively halogenate the methyl position, and then the hydroxide can attack in, kick off your leaving group, and you quench it with acid. So let's make a note of that. That's where you have NaOH, Br2 in excess, followed by an acid workup. So those are a little bit different, but similar. All right, we also had alpha halogenation of carboxylic acids. Does anybody remember the name of that reaction? I think Paul remembers. What do you call this reaction? Come on. The Hell reaction. The Hell-Volhard-Zelinsky reaction. So this is PBr3, Br2. Followed by H2O, and this is a really nice reaction for brominating the alpha position of carboxylic acids. Okay, we also saw halogenation, or sorry, not halogenation, alkylation of the alpha position. And there were a handful of alkylation reactions we saw. Oh yeah, sorry. There's one alkylation where you can alkylate the more substituted carbon, and then there's one where you can alkylate the less substituted carbon. Which conditions would you need for each? Let's do the top one first. Do we want a big base or a small base for the top one? Small base. We need to be able to get into that nook and cranny to get that proton, so we use sodium hydroxide. And then we use an electrophile that's typically a methyl or primary electrophile. What temperature should this be run at?
Hot.
Room temperature. Or hot, either one's fine. All right, what base is commonly used to alkylate the less substituted carbon?
LDA.
LDA. And then what temperature?
-78.
-78. That's our dry ice acetone bath.
What happens if there's not -78?
Then you get a lot less regioselectivity. You might get alkylation at both positions. So by cooling it way down, you're going to favor alkylation at your less substituted carbon.
Are you going to show the test if you want the less substituted, you're going to show -78?
Yes, exactly. If I want the less substituted one, I will indicate that it's very cold. All right, there were a few other alkylation ones we saw. We saw the reaction with diethylmalonate. And when we did this reaction, you got a carboxylic acid with some sort of R group coming off of it. What was the first step for this one? Yeah, sodium methoxide. You want to use the same base as the leaving group for your ester. So we deprotonate, then we alkylate. And then step 3, we've got to blow off CO2 and convert our ester to a carboxylic acid. What do we need there? Yeah, just acid and heat. But you can see all of these involve functionalization of an alpha carbon next to a carbonyl, right? In this case, you can only make an alpha functionalized carboxylic acid. Let's do the next one. It's closely related. It's the ethyl acetoacetate. And with this one, you get an alpha alkylated ketone. And same sort of thing. We use sodium methoxide, the same base that's our leaving group for our ester. We don't want any transesterification. Then we do an SN2 reaction for alkylation. And then in step 3, we treat this with acid and heat. Make sense? This was pretty much all of the alpha functionalized reactions that we saw, but we did see a lot of beta functionalization. Okay, for beta functionalization, the first one we saw was with conjugated carbonyls. How would I accomplish this transformation? Assume the R is a carbon. Could I just throw in a Grignard? No, what's the problem with the Grignard? It's too powerful. It'll attack the carbonyl carbon. So we need a less powerful reagent. Typically a weaker nucleophile will do conjugate addition. Which nucleophile do we need? Not quite. Yeah, exactly. The lithium dialkyl cuprate. The storic enamine is a nice way of making a weak nucleophile. But in this case, we just want a basic carbon nucleophile. So R2CuLi. H2O. Really, any weak nucleophile will work. But all of these will deliver the nucleophile onto the beta carbon, not onto the alpha carbon. All right, the next one we saw I'm just going to draw out both equivalents. Was our aldol, where you take sodium hydroxide and some sort of ketone or aldehyde, usually an aldehyde though. And if you keep it cold enough, let's even put cold here, you'll get a beta hydroxy ketone or an aldehyde, but again, you're functionalizing that beta position. And then we said if you want, you can apply heat. And push this all the way to the alpha beta unsaturated ketone or aldehyde. So if you do want to stop at the aldol addition and not the condensation, you have to run the reaction cold. Does that make sense? All right, and then one last one was our Claisen condensation. And I'll just make these simple. Where again, similar to the aldol, but this time your beta position now contains a new carbonyl. The neat thing is you can do further chemistry on this, right? We know how to protect ketones and aldehydes selectively over esters, and then we can do reactions on the ester, deprotect, and then so on. So there's a lot of reactions we can go off of, but these were kind of the key ones from the chapter. I know this chapter has a lot of weird reactions, so in the course notebook, I've got the summary of reactions from the back of the textbook. Make sure you're comfortable with the full mechanisms for all of these, including the intramolecular reactions. And then if you really want to go through and test yourself too to make sure that you're comfortable, I've got a fill-in-the-blank study guide that's from the solutions manual. So you can go through this and print it off and fill it out almost like flashcards if you'd like. I know this has helped some people in the past. But what I think we're going to do at the rest of today's time is go through the synthesis worksheet. I will admit the synthesis worksheet is more difficult than our standard synthesis worksheets. So I would recommend getting together with a small group, push tables together. You're welcome to come up and use the whiteboards too. So if you guys want to cluster around whiteboards, you're more than welcome to.